Yeah. Hi everyone, we're going to go ahead and get started. Our seminar speaker this week is Dr. Stewart from UCLA. He's going to be talking to us about his research on feedbacks on ocean circulation and ice melt in Antarctica. I'll let him push it on.
Thank you very much, and I hope everyone can hear me on Zoom. I'm trying to figure out how to operate this microphone best. If you can't hear me on Zoom, please somehow let me know, and I will adjust. Hi everyone, it's nice to see you all here, and it's been great to meet you as members of your department today. This is my first ever visit to UCL. Thank you very much for inviting me to come down here. It's been really great to get a week on campus and actually do some in-person meetings and give an in-person seminar after so long. I don't think I need to remind anyone about the harrowing last 3 years, so I'll move right today to talk about isolating feedbacks between polar ocean circulation and ice melt. So this topic, the interaction between the ocean and the ice shelves around Antarctica, is one of the main areas of research in my group at UCLA. And today I'm going to tell you about a couple of topics that some of my recent and one of my current graduate students have been working on in this general area. And before I do that, I'm going to give you some general background on the topic of ice-ocean interactions around Antarctica, high-level motivation, and talk briefly about this topic of feedbacks between melt and ocean circulation. Okay, so you can't see the pointer on the screen. Okay, so I'm just going to have to sort of gesture at things, and hopefully you'll know what I'm talking about. So the high-level motivation for much of our work, as you probably know because we have some very prominent high-expert scientists in this department, is that there is an accelerating rate of mass loss from the Antarctic ice sheet. So this figure on the left here shows us various important components of this system. It shows us the temperature of the ocean at the sea floor around Antarctica. That's the colours. It shows us the rate at which Antarctica's ice shelves are melting. So these are places where the Antarctic glaciers actually float on top of the ocean and are in contact with the ocean. And those are the colours of the yellow or red colours of the bits around the coast. And then also it shows us the rate at which the actual grounded ice, i.e. the ice that's not floating, that's not in contact with the ocean, is being lost. So those are the grey circles. And you can see that there is a general correspondence between these three things. The places where the temperature around Antarctica is warmest, up in the shallower parts of the ocean on the continental shelf, are the places where there is a most rapid melt of the ice. This is not entirely surprising. It's not guaranteed that this would necessarily lead to more loss of ice from inland, which ultimately has a greater impact on sea level rise, but it does also tend to be the case that the places, particularly in West Antarctica, in West Antarctica, I can very slowly move this to here. In West Antarctica, where the ice shelves are most rapidly, do also tend to be the places where mass is being lost from inland as well. And the consequence of all this that they're interested in better constraining and understanding the underlying causes of is that it's projected to lead to increases in or contribute to future sea level rise. So these figures on the left and the right, show some projections of future sea level rise from Antarctica from an ice sheet model, going to 2100 on the bottom and 2500 on the top. This particular model tends to produce projections that are somewhat extreme compared to some other projections. I understand this is because of the way it handles some parameterizations of certain instabilities that occur in the ice sheet dynamics, but still it's to give you a sense that there are projections out there of contribution to sea level rise, global mean sea level rise, 1 meter by the end of the century. Obviously, though, there is a great deal of uncertainty and a large spread of these projections across different models. The final thing I'd like to highlight in this slide, which you can see in the left-hand figure, is this separation between the relatively warm waters offshore and the cold waters around the Antarctic coast. So this is a relatively sharp barrier between different water masses in the ocean, called the Antarctic slope front, associated with the westward flowing current called the Antarctic slope current that almost entirely encircles the Antarctic continent. and the exchange of heat across this slope front or slope current system is of primary importance for the melt around the Antarctic margins, and we'll come back to that particular feature later in the talk. Another high-level motivation for better understanding Antarctic shelf processes is that they are directly connected to the global abyssal overturning circulation. This top panel here is likely a schematic you've seen some variant of before. It shows schematically the pathways of the ocean circulation in a zonally averaged view. And the branch of this that's of particular relevance to this top is the branch indicated by the blue arrows, which is supplied by the formation of dense waters around the Antarctic continental shelf. The plot on the bottom, which I will walk through in great detail, measures how much of the subsurface ocean is supplied by different parts of the ocean surface, and highlights that these few sites, particularly in the Ross and Weddell seas around Antarctica, are supplying roughly a third of the global subsurface ocean. They're sort of filling about 1/3 of the global surface ocean, if you like. And this rate of water mass injection, and therefore the deep circulation, is quite sensitive, therefore, to changes in the processes occurring on the Antarctic continental shelf, which in turn are in fact quite sensitive potentially to changes in the rate at which the Antarctic ice sheet is melting. So there's a couple of major reasons with global implications to be concerned about Antarctic continental shelf processes and melting of the Antarctic ice sheet. So how do we end up with water in the ocean getting to the bases of Antarctic ice shelves and causing this melt? So this is a schematic that summarizes the major mechanisms by which the ocean comes to be melting Antarctic ice shelves. There are three principal mechanisms by which this occurs, and the one that I would highlight in particular is the transfer of this relatively warm water mass. By warm, I mean maybe 2 degrees Celsius, from mid-depth offshore in the deep ocean around Antarctica onto the continental shelf, and then toward the undersides of these floating ice shelves. So just as a reminder here for sense of scale, this ice shelf is typically in the order of 500 meters thick, perhaps. The ocean beneath it, the ice shelf cavity, we might call it, is also typically in the order of 500 meters thick. And these ice shelves span areas of maybe 100 to 500 kilometers in horizontal dimensions. So these are large areas of ocean with substantial vertical extent. Here is actual measurements from the continental shelf break on the left, all the way to the back of one of the most well-known ice shelf cavities, that of the Pine Island Glacier. Is well known because it is melting particularly rapidly. And you can see why from these measurements, which were made using a specialized piece of instrumentation called AutoSub, that's able to traverse large distances beneath these ice shelves without being directly in contact with ships. This layer of relatively warm circumpolar deep water you can see in the red in this diagram, in this plot, can be seen intruding beneath the ice shelf, which is way over there, and getting all the way back to the back of the ice shelf cavity, the grounding line of colour, where it's in contact with the ice and is inducing this relatively rapid melt. So, an important question that comes about when understanding not only how this melt comes to happen, but how the rate at which the melting is occurring will change in the future, is how does the heat get from the open ocean, where it's abundant, to back to these ice shelf cavities, where it can be the heat can be extracted and melt can happen. This plot here is actually taken from a very high resolution ocean sea ice model run by NASA. It's a snapshot of the ocean temperature at 500 meters depth, or at the seafloor at depth, where the ocean depth is shallower than 500 meters. And you can see, first of all, that there is indeed much warmer water around the outside of this plot than there is around the coast. And I'm sorry, there's no color bar here. That is my fault. That should be there. There's water around the outside is around 2 degrees Celsius, and the water around the coast is about -2. And you can also see that the the ocean around Antarctica is very full of structure. There are many, there's a great deal of large-scale structure, but also fine-scale structure down to scales of it in the simulation on the order of a few kilometers, taking the form of mesoscale eddies. So all these swirls and tiny blobs you can see in this plot are small vortical structures, and those are going to be an important topic of this presentation later in the talk. In this particular study, which I don't know if the citations dropped off the bottom here, which we published in 2018, we used the simulation to look into how it is that you actually get heat from offshore onto the continental shelf. This simulation does not explicitly represent the contact between the ocean and the ice shelves themselves, but it does represent the continental shelf, and so we were able to use it to get some insight into how this happens. And without walking through the details of the study, because it's not the focus of this talk, essentially we broke down the rate at which heat is being moved onto the continental shelf, in here, plotted from many different sectors of Antarctica, into contributions from the sort of persistent flows in the ocean, the mean circulation, and these swirling eddies, and also from Antarctic tides. And the takeaway, what we found in almost all sectors of Antarctica, was that it's actually these eddies, these swirling vortical flows in the ocean generated by horizontal gradients in the density that are carrying heat across the shelf break and onto the continental shelf. And this is important because you actually need rather fine model resolution to accurately represent these structures. They occur on scales of just a few kilometers, which imposes a very tough constraint on any models that seek to explicitly represent them. And it actually also turns out to be rather tough to accurately parameterize their effects. And we'll see later that actually accurately resolving these eddies may be quite important to accurately capturing feedbacks between the melt and the circulation of Antarctica. So another sort of context point I'd like to put in your minds before we move further in the talk is that Antarctica, and maybe it's an obvious point to make, Antarctica is quite a heterogeneous place. The Antarctic coast and its contact with the ice shelves has a wide variety of flavors. When we reviewed this subject in 2018, we broadly characterized the hydrographic structure of the Antarctic continental shelf into three regimes. In retrospect, this is one of those things where I published it, and in retrospect, I look back and think that was really rather crude, but a lot of people in the community have kind of run with it, so I guess we're stuck with it now. And so we said there are primarily three major regimes or flavors of continental shelf around Antarctica. The fresh shelves, where the ocean is cold and fresh in the continental shelf, and you have a relatively strong barrier between the warm waters offshore and the cold waters of the shelf. The dense shelves, where dense waters are formed by new sea ice formation and cascade off the shelf into the deep ocean. And the warm shelves, where there seems to be seemingly free access of these offshore warm waters onto the continental shelf, and this is associated with rapid melt of low ice shelves. I'm also putting this in your mind because later in the talk, I'm going to come back to these different regimes and show that the response of heat fluxes onto the continental shelf and thus towards the ice shelves can be quite different depending on which of these regimes you're already in. So the final point for this introduction that I'd like to make is to do with changes in the state of the Antarctic continental shelf and the rate at which ice is melting. Much attention has been given in the recent literature to what drives changes in these circulations and the rate at which the ice shelves are melting. And the sort of go-to mechanism for driving these changes is changes in the wind. Changes in the winds in the southern hemisphere is one of the most conspicuous signals of recent anthropogenically driven climate change. In particular, the westerly winds that made latitudes have been shifting to the south. And the impact of this for Antarctica is that it is projected to weaken the winds that blow to the west along the Antarctic coast. Now, this prominent paper from Spence et al. 2014 argued that if we shift these westerly winds to the south and weaken the winds that are along the Antarctic coastline. So in other words, we shift these winds that are going to the west on the Antarctic coastline further south. It's going to weaken the shoreward transport of water by Ekman transport in the ocean, which currently serves to push cold fresh waters onto the Antarctic continental shelf and keep the warm waters offshore, prevent them getting onto the continental shelf. And if we weaken those winds, as is expected to happen in the future, then that effect will be weakened and we'll have less cold fresh water being pumped into the shelf, and so warm water will get on more easily. And so we expect more melt to happen. And this related, a very closely related mechanism has been intensely studied in the context of the West Antarctic ice shelves, the particularly rapidly melting ones I showed you earlier, like the Pine Island ice shelf, where these authors in particular at the top here have made the argument that at times when the winds have been blowing strongly to the east, we have seen relatively rapid acceleration of the melt in these ice shelves, and then whereas the melt has not increased so rapidly at times when the winds have been blowing to the west. Now, I don't think that conclusion is super obvious from this figure. If you consider that to be a tenuous conclusion, I think I might be inclined to agree with you, but there is mounting evidence that there indeed may be a wind-driven mechanism for changing the melt rates of these ice shelves, and in fact that these melt rates might be further tied by teleconnections to the equatorial Pacific. Another driver I might mention is that we've also seen from measurements around Antarctica that the depth and temperature of that warm water that surrounds the continent have both been changing, so that the water has been rising and it's also been getting warmer. And so this might be related to changes in atmospheric forcing as well, or might be an independent result of far-field changes in the ocean. Other drivers I have mentioned here might include, for example, changes in precipitation. Will change the salinity of the Antarctic coasts. In addition to these, what might be considered external drivers of change around Antarctica, there are also changes to be expected in the near Antarctic circulation resulting from changes in the melt itself. Melting of the ice shelves injects fresh water around the ocean, into the ocean around Antarctica, which increases the buoyancy of the ocean and is a mechanism of forcing changes in the circulation. And so this gives rise to the possibility that changes in the rate at which the ice shelves are melting will change the circulation of the ocean, which may in turn again change the rate at which the ice shelves are melting, and therefore there's a possibility for a feedback between those two things. And I'm not the first person to suggest this. Various previous papers have noted that this possibility exists. I'm going to mention a couple here. This one about Gomez et al. In 2019 ran an ice sheet model and an intermediate complexity Earth system model, and an experiment in which they did and did not allow the melt from Antarctica to feed back on the ocean circulation. And what they found was that if you allow the melt to feed back in the ocean circulation, it tends to form a freshwater layer around the margins of Antarctica that traps heat beneath the surface and raises the temperature of the waters around Antarctica, and thus induces further melt. So comparing the panels on the left and the right, left is no melt feedback and right is with melt feedback, and allowing the melt feedback in the circulation increases the rate at which sea level rises in this model. The second example, I would say it might appear to contradict the first, but it doesn't really. I think that mechanism that I just described still holds in this lower, in this paper below, except for they have allowed for, in the second paper, they performed a conceptually similar experiment that allowed for additional feedbacks between the melt and the ice. In particular, they found that allowing for melt feedback increased the amount of sea ice around Antarctica, which tended, and also reduced the amount of hyperfracturing, and actually resulted in a negative feedback. They found that allowing meltwater to feed back on the circulation of the atmosphere and ocean actually reduced the net sea level rise in the long run, in this case out to about 2250. So, first of all, it's not entirely clear whether the effect of melt on the ocean and atmospheric and sea ice circulation will have a positive or negative feedback in the long run, and it's important. So you can see the magnitude of these changes is actually not dissimilar to the long-term change in sea level itself. But more and more fundamentally, we don't really have a good handle on the nature of these feedbacks, in part because, to a large extent, we have not previously been able to reach the scales of motion at which important processes occur around Antarctica. So the two studies I'm going to present to you over the remaining slides at this talk are going to aim to isolate two of these melt circulation feedbacks around Antarctica, and with the aim of better understanding how they function, with a view to kind of better informing these modeling studies such as these, which aim to quantify the impact of these feedbacks in long-term changes in sea level rise. So the first of these two studies is called Biostability of the Flux from an Ice Shelf Cavity Circulation and Bathing Out. It was led by a graduate student of mine called Julian Hazel, who graduated a couple of years ago. And the additional context that you need to understand this piece of work is that it turns out, perhaps counterintuitively, that some of the parts of Antarctica in which the most heat is transported onto the continental shelf and toward the ice shelves turn out to be those where the continental shelf is actually coolest. So this particular study here by Morris and al. 2020, they used a relatively high resolution ocean sea ice model to look at where heat is moving onto the continental shelf around Antarctica. In fact, more precisely, they looked at where this warm water mass called circumpolar deep water moved onto the continental shelf around Antarctica. And to cut a long story short, what they find is that this heat is actually moving onto the continental shelf in a few key regions: the Ross Sea, the Weddell Sea, and Prince Bay, which are labeled in the upper right panel of this plot, which actually shows the cumulative amount of heat of this water mass moving onto the shelf as a function of distance around the continent. And the defining feature of these three regions is that they are all dense shelf regions. They're all very cold, and the shelf is very dense. Now, that might seem counterintuitive because the rate at which the ice shelves melt in those areas is very low. But it's really not counterintuitive because the amount of heat that's extracted from the ocean by the atmosphere in those regions is very high. And it's actually the formation of these dense waters in the shelf that cascade off into the deep ocean that are driving this warm water onto the shelf. But this heat that's getting onto the shelf from these regions is not all just being absorbed by the atmosphere. We do observe this heat reaching the ice shelves. For example, the one that we're going to focus on is this one shown in the map here. It's called the Filchner-Ronne Ice Shelf, or FRIS, in the southern Weddell Sea. It's one of the two largest ice shelves around Antarctica, or ice shelf systems around Antarctica. And in this study just published this year, it's one of the latest in a series of studies to show that this warm circumpolar deep water CDW from offshore is reaching this ice shelf, and in fact is extending a substantial distance into the ice shelf cavity and inducing melt. And the actual amount of this heat that's reaching the ice shelf and versus being extracted to the atmosphere by the atmosphere is not well constrained, and nor is what controls that partitioning of the fate of the heat well understood. Furthermore, there are some concerning projections that have shown that this particular ice shelf might undergo a dramatic shift in its behavior in the coming century. This study by Helmer et al. In Nature in 2012 predicted that changes in the circulation of the atmosphere around Antarctica would redirect warm water from offshore onto the continental shelf about mid-century, resulting, as you can see in these more panels here, showing the temperature on the continental shelf and within the Filchner-Ronne ice shelf, divided by this grey line here, you would end up with warm water intruding into the cavity and increasing the melt rate of this ice shelf by a substantial amount. In fact, the amount by which this single ice shelf increases its melt in these simulations is equal to about half of all of the melt going on in all ice shelves around Antarctica right now. So this is a potential for a huge shift in the behavior of this particular ice shelf, and in fact for the circumantarctic integrated ice melt. And perhaps even more concerning, in a follow-up study, they found that if this process started, if warm water started intruding into this ice shelf cavity, they found that it was very difficult to make it stop. So they ran a series of experiments indicated in this top panel here, these time series of melt versus year, where they kind of spun off new experiments at different times in the 21st century, in which they reverted the atmospheric circulation to present-day conditions. And in fact, they found that under no circumstances could they revert the melt rate back to present-day conditions. It always ended up being extremely warm and continuing to melt at this greatly elevated rate. So this suggests that the melt of the ice shelf itself is fundamentally changing the circulation and behavior of the local continental shelf. So, to investigate this possibility, Julia created this regional model configuration of the southern Weddell Sea and approached on the ice shelf. You can see a map of the model domain here. I won't bore you with the technical details of this model simulation. It suffices to say that it's a simulation of the ocean and sea ice state around Antarctica, with static ice shelves. I'm sorry to disappoint the glaciologists here. So the ice shelves are fixed, but they are able to melt without changing their mass, and therefore provide a force into the ocean. It's forced over a 9-year repeating period by atmospheric state estimate, and with boundary conditions from an ocean state estimate. I'm going to jump straight into what I think is the most interesting part of the findings from this model. And so what we want to investigate is the potential for feedback between the melt and circulation to be, or feedback to the melt to be fundamentally changing this ocean circulation and somehow making it difficult to revert the state of this ice shelf back to pre-industrial conditions. What I'm going to show you here is results from 2 experiments with this regional model. These experiments are identical. They have identical boundary conditions and model parameters and durations and forcings from the atmosphere and everything. And the only difference between these 2, ref on the left and fresh on the right, is that they are initialized with cavities, ice shelf cavities, with different properties in the water. So in the reference case on the left, the water in the cavity is initialized with a salinity of 34.45 PSU. The number doesn't really matter. The point is it's relatively salty and relatively dense. On the right, there's a fresh simulation. The cavity is initialized with a salinity of 34 PSU, so relatively fresh. Otherwise, all the forcing of the model is identical, and the result is completely different. So what we see on the top panels is the temperature at the seafloor in the model after it's reached equilibrium with its forcing, averaged over a 9-year period. And then at the bottom, we see the rate at which mass is being lost, so the melt rate in meters per year of the ice. And for, again, identical forcings, everything is identical except the way the model was initialized. And on the right, we have a order of magnitude larger net melt of the ice shelf. So here we have a situation that strongly suggests a bistable regime, right? We have identical, think of this as a boundary value problem, we have identical boundary conditions and yet 2 different possible states, or at least 2 possible different stable states, which are really dramatically different from one another. These time series actually quantify those differences, and the most interesting ones for us to think about are the top, which show us for the fresh case in red and the reference case in blue, the average temperature in the ice shelf cavity. The details of this diagnostic are not worth getting into unless you really want to. Essentially, it's the temperature of the water in the cavity where the melt is happening. And the bottom shows the actual total melt rate of the entire ice shelf. And what you can see is that on average, the temperature of the waters in the cavity in the important places are about a degree warmer in this fresh simulation, and the melt rate is about an order of magnitude larger in that case as well. So it's a huge qualitative difference in behavior. So there's multiple questions possibly in your mind right now one of the questions, and hopefully I'll cover them as much as I can, one of the questions we had is, how can you make the model, or nature perhaps, transition between these two states? What can kick the filtering on the outside cavity between from one of these states to another? So we ran a bunch of, actually really rather extreme perturbation experiments to try and figure this out. I'm showing you a subset of them here. From now on, just for clarification, I'm going to refer to this situation on the right, where the cavity is very warm and the melt is high, as a warm case. And the situation on the left, where the cavity is cold and the melt is low, is a cold case. So that's an important piece of nomenclature. We ran a few experiments where we started them, the experiments from the end of the simulation, the end of the reference simulation, the end of the warm simulation, or the end of the cold simulation, or the end of the warm simulation, and gave the model significant perturbations to the atmospheric state, looking for ways in which changes in the climate of Antarctica might induce shifts in this behavior from one state to another. And the answer, it turned out to be, it's actually, for the most part, quite hard to induce a shift from the one to the other. For example, this red curve, orange curve, shows a simulation in which we started the model in a warm state and then decreased the atmospheric temperature by 30 degrees Celsius, and it doesn't change to the cold state, because sea ice is a very effective insulator, essentially. The light blue curve shows one in which we entirely turned off east to west winds. We expected to turn off east to west winds, as we discussed earlier, to allow more warm water onto the shelf, but as you can see, the melt rate of that situation, of that case, is very low. In contrast, the red and dark blue curves show simulations where we perturbed the offshore winds by relatively small fractions, minus 50% in the blue case and plus 20% in the red case, and that was sufficient to cause this model to shift its state from the warm to cold or cold to warm over a period of about 25 years. So this suggests that this behavior, this biastability, is closely tied to some processes relating to offshore winds, and I'll explain why that is in a couple of slides. What this set of experiments motivated us to do was to see if we could trace out the full parameter space of this this bistable regime in the behavior of the filtering on the ice shelf cavity via a series of these regional model experiments. So Julia ran many realizations of this regional model, and the curve at the point on the top is the key one here. It shows every single point is a different experiment run for several decades with this regional model. Every experiment with a red dot was started with a warm cavity. Every experiment with a blue dot was started with a cold cavity. And then the x-axis is the factor by which we perturb the offshore wind. So one is the reference, like nature today, our best guess, and then large numbers are stronger winds and smaller numbers are weaker winds. And what you can see is that over a substantial range of these offshore winds, the model, at least, is bistable. The outcome depends on the initial conditions. If you start in a warm state, you finish in a warm state. If you start in a cold state, you finish in a cold state. In contrast, if you make the winds strong enough, then regardless of how you initialize the model, you always end up in a cold state. If you make the winds weak enough, regardless of how you initialize the model, you always end up in a warm state. So basically what this traces out is a hysteresis movement. And it tells us that, for example, if you start in a situation that we think is like today, like this case here, and this black dot, if you make the winds weak enough, about 30% weaker, then you may abruptly transition to a condition that has an order of magnitude increase in the basal melt and a much, much warmer cavity. But if you want to get back to a condition that resembles today, back to a cold cavity, you have to make the winds way warmer, even warmer than they were when you started, in order to get back there. And this is why this change in the regime of the ice shelf cavity, the change in the rate of melt, is apparently irreversible. You have to go to a sort of even colder climate than pre-industrial in this model in order to make the model revert to a cold cavity state. wondering, in the interest of time, I should move on to the second topic, but briefly, the explanation for all of this. We posed in the form of a reduced order model for the whole system, and it comes down to the fact the relationship between this behavior and the offshore winds is that these winds off the coast of the ice shelf are forming new sea ice and injecting salt into the ocean, and they're making this dense water around the front of this floating ice shelf called high salinity shelf water. And in the present day, this water is much denser than the warm water that sits offshore, and this is why the warm water doesn't flood into the cavity and melt, because there's already denser stuff on the continental shelf that kind of blocks it off. And our conceptual model of how this works is that it's a competition between these two water masses. If this water formed by sea ice formation, high salinity shelf water, HSSW, is denser than this warm water offshore, then the high salinity shelf water fills up the cavity and the cavity melts slowly. If the warm water is denser, the warm water fills up the cavity and the cavity melts quickly. Which is all, which I think is fairly unobjectionable. But where the feedback comes in is that the properties, the density of this high salinity shelf water isn't just influenced by the rate at which sea ice is formed, it's also influenced by the melt. And this is expressed conceptually by this equation at the bottom. It says it's got the salinity of that water, so essentially the density, is equal to the salinity of some source water plus an increase due to salt input from sea ice formation minus a decrease, a dilution because of melt from the ice shelf. And if this melt term becomes large enough, or if this increase from the linear from salt to the sea ice formation becomes small enough, you might make high salinity shelf water so light that it's no longer denser than the warm water offshore. At that point, the warm water floods the cavity, the melt rate goes up by a lot, and all of a sudden the high salinity shelf water is way lighter than the warm water offshore, and you need to increase the winds by just a ton in order to get back to a state where the high salinity shelf water is denser again. And we tested this mechanism, this model, crude model, against the diagnostics from our regional model, and they kind of qualitatively agree. But I don't consider this to be an impressive prediction because it's largely tuned on the model in the first place. It's merely an explanatory conceptual model for what's happening. So the takeaway, I think, from this study was that, first of all, this is evidently an example in which feedback between the melt water from melting ice shelves and ocean circulation is a huge contribution to setting the state of this system. I mean, the change in the rate of melt due to this melt water feedback is way larger than the forced response in any of our experiments. So I think it's sort of demonstrably an important facet of the Antarctic ice ocean system that needs to be better understood. The key player in actually switching between states is the strength of the winds blowing off the Antarctic ice shelf, but it's not the only thing that can make these cause these changes to happen. We didn't find it was the case, but other subsequent studies have found that changes in the depth of the warm water offshore can be influential as well. But it opens a question as to whether this kind of behavior might manifest in other Antarctic ice shelves. And actually, honestly, I kind of hope not, because it would be very worrisome if many Antarctic ice shelves were able to undergo this kind of dramatic switch in their melt rates. It could give rise to some tipping points in Antarctic ice shelf behavior, potentially. And so we've been trying to better understand this, rather than try and simulate every single ice shelf in a different regional model. One of my current students has been playing with some more kind of generic ice shelf ocean models to better understand this behavior. But there's even more complexity here because no ice shelf is an island. The behavior of one ice shelf, the waters produced from one ice shelf can easily influence the behavior of adjacent ice shelves, and the extent to which that occurs is only just beginning to be explored in the literature on near-Antarctic circulation and ice ocean extraction. The second study, which I realize I'm a bit short on time for, is called Heat Transport Across the Antarctic Slope Front, controlled by cross-slope salinity gradients. And this is a study by my senior graduate student, Clara Su, and it's currently subject of a manuscript in review. I will give a kind of executive summary of this study in order to not go too far over time in this talk. I think that one of the slides I will tell you about is this one. It's one of the high-level motivation. And I'm going to bring us back to this question of melt feedbacks, bring us back to this study by Gomez et al. I mentioned at the start of this talk. And this study, among many others, have put forward the idea that when you inject melt from around Antarctica, it tends to stratify the upper ocean and trap heat below the surface and actually end up heating the continental shelf. And you can see that in this temperature anomaly plot from their modeling work. So this, again, this has been multiple studies cited here, and almost all of these studies tend to be studies based on kind of IPCC class climate model type models, generally rather coarse and horizontal resolution. And an interesting counterpoint to this finding came in a recent paper by Ruth Moorman now at Caltech, who ran a high resolution, so I think it was a 10th degree model for admittedly a relatively short period of time, in which they investigated the feedback of meltwater on near Antarctic ocean circulation by just injecting additional meltwater around the Antarctic coast. And they found a contradictory finding, which was that most of the Antarctic margins, and I'm only showing you the schematic summary of their work rather than dig through all the figures for you, but happy to show you more if you like. Most of the Antarctic margins, in response to meltwater forcing around the Antarctic coast, did not get any warmer. And in fact, key regions where the ice shelves are melting the fastest in the West Antarctic area over here actually cooled in response to the injection of meltwater, which suggests that there might be a negative feedback, that you might, injecting meltwater in Antarctica, if you resolve the coastal waters well enough, actually seems to isolate the coastal waters from the offshore ocean and actually make it even harder for warm waters to get under the continental shelf. So this suggests an entirely different behavior, that there could be a negative feedback purely in the ocean by isolating the continental shelf and preventing more warm water accessing the ice shelf. So which is it? The short version, which I think you probably appreciate at this time in the seminar, is that we've run some targeted simulations to look at this, and those simulations fully resolve the mesoscale eddy field. And the answer is we do find a positive feedback, but it's not for the reason that's advocated in the studies listed above. It's because when you inject more meltwater around the coast, you strengthen the gradient of the density between the coastal waters and offshore, and this actually strengthens the rate, increases the rate at which eddies grow, and increases the efficiency with which they move heat onto the shelf. So rather than being a kind of subsurface heat trapping mechanism, it's actually an intensification of eddy transport onto the shelf. So the short version of the study is that we think it's a positive feedback, but it's possible that these studies listed there are getting the right answer for the wrong reasons. Although we can't really say for sure until we can investigate this in a model that can accurately represent the Antarctic system and resolve the eddies. So in the interest of a condensed presentation, I'll tell you that we obtained these results by constructing a model that is able to resolve these eddying motions, which actually requires us using a rather fine grid resolution, and therefore restricts us to using a relatively idealized representation of the transition between the open ocean and the Antarctic continental shelf. And you can see the geometry of the model domain here. It's a very focused, localized model domain, and it's being set up in these two model configurations visualized here to capture some of the relatively extreme situations we observe on the Antarctic continental shelf in the present day. So on the right, the so-called fresh shelf regime, where the continental shelf is very fresh, the blue, the colors are salinity here. And on the left, the dense shelf regime, where you have much denser water on the continental shelf than you do offshore. And stepping through the results quickly, one key take home I want you to take away from this is if we run a series of experiments in which we just fix the salinity on the continental shelf, just take that as a control parameter, and examine how the amount of heat moving onto the continental shelf varies with that salinity, what we find is that actually making the continental shelf denser or saltier or fresher increases the rate at which heat is transported onto the continental shelf. So our reference case for this set of experiments is this black dot way over here, or I'm going to not talk through the left plot unless you particularly want me to. And this plot quantifies the rate of heat transport onto the continental shelf as a function of that shelf salinity. So in this reference case, there's approximately no gradient in the density between the open ocean and the shelf. And as we make that density gradient larger in either direction, the rate at which heat moves onto the shelf increases, particularly when we make the shelf denser, but also when we make the shelf fresher. And Clara has indicated this as a positive feedback, even though the model cannot explicitly represent the positive feedback, because the anticipation is that if you increase the shoreward heat transport onto the shelf, that would further increase the melt. But of course, that's not a guarantee, and remains to be tested. Another important point is that if you try to capture this in a lower resolution model, so these additional lines that plotted here show models at lower resolution that Clara also ran, you do not capture this effect. Actually, you do capture the effect of making the shelf denser on the right, but making the shelf fresher, you do not. So about 5 kilometer resolution is about the resolution used in that Merman et al. Study, where they found that the shelf was isolated by additional freshwater input. But even that is not enough. You really need to be down in the order of a kilometer in horizontal resolution to capture this effect, which is really not great news for us as Antarctic modelers. But this unfortunately is just a threshold imposed dynamically by the scale at which these eddies tend to emerge. I will not talk through the slide, but the gist of it is that the heat transport occurs through very different mechanisms in these different cases. I think I can succinctly summarize the findings using this schematic on the last slide here, which shows how the behavior changes as we move from a reference case where there's essentially no shore heat flux because there's no gradient in density between the shelf waters and offshore. And we move toward a situation where the shelf is fresher than the top, or we move toward a situation where the shelf is denser on the bottom. If we make the shelf fresher, then what happens is baroclinic eddies grow on this gradient of the density between the shelf and the open ocean and transfer heat onto the continental shelf. And this, the heat transfer gets stronger and stronger the larger the density gradient is, and thus the potential for positive feedback. In contrast, in as we make the shelf denser, we actually create dense overflows that cascade down in canyons. And it turns out that these dense overflows are relatively well represented even at lower model resolutions. So actually this, what we might call negative feedback, is actually cannot be adequately represented in lower resolution models. And essentially what's happening here is it's a simpler process. Stronger density gradients between the shelf and offshore drive stronger dense overflows, which pump more heat up into the continental shelf, consistent with previous studies. One of the issues with these findings is that although we've ultimately come down to a conclusion as to whether there should be a positive or negative feedback between changes in meltwater discharge and heat transport onto the shelf, we've been restricted to use a rather idealized modeling framework by the restrictions imposed by the resolution requirement. And the translation to the really real heterogeneous Antarctic margins remains unclear. We are trying to rectify that. We're in the process of developing a circular-Antarctic model. There's some snapshots of bottom temperature and meltwater from that model, but Clara is leading the model. We are in the process of trying to push this model down to the kind of resolution we think we need to fully resolve these eddies. We think it's about 1/24th of a degree. It's just so expensive and data heavy. But this is what we think we need to solve the problem, so that's where we're trying to go. Finally, just to wrap up the talk, I'm not going to be able to talk about this as much as I'd like to. I also want to just mention that we don't necessarily only think about Antarctica, we've also given some thought to Greenland as well. And these melt ocean circulation feedbacks turn out also to be rather important there. This summary slide advertises the work of Ken Jha, who's now a massive postdoc fellowship at OSU, having graduated from our group about a year ago. And he has been shown the fact that the feedback between the melting of marine terminating glaciers in fjords and the circulations in those fjords is also an important melt circulation feedback. And in this particular example, we've been creating a whole suite of fjord simulations that are essentially forced only by subglacial discharge and melt at the faces of the ice sheets in these fjords. Produce quite an exotic range of behaviors and circulations, and these circulations, these various eddies that you can see appearing, actually then feedback on the melt of the ice itself. I won't go further in describing this work, but I do recommend reading about Ken's work because it's also very interesting. So with that, I'm going to finish here, and thank you all for your attention.
To what extent are you worried in your very high resolution model that you'll be able to do only one run? And you told us that the initial conditions matter a lot in the outcomes. So will you be left wondering, or you're not worried for some reason?
I'm worried about many things in my life. And one of the ways we are trying to save ourselves from catastrophe of the kind you described is that we've been spinning up the model at successively higher resolutions from 3rd to 6th degrees, 12th degree. In that way, we're kind of, getting a sense of whether we're headed for disaster before it happens. I mean, there are many. A bigger issue that we've been facing is just dealing with biases. There's many ways in which you can end up with significant biases, and the catastrophe of the Oceanic ice shelf melting dramatically is just one of the more dramatic examples of those biases. But even just getting the whole circumantarctic region to look qualitatively correct, recommend quantitatively, has been hard because you're relying on a lot of parameterizations of, for example, processes that exchange heat across the ice ocean boundary layer that don't necessarily work universally in different ice shelves, and uncertain parameters of behavior of sea ice. There's many things that can introduce biases, and we've been struggling with compromising on a simulation that is adequate without being perfect.
You have a question soon.
Yeah.
You can ask your question, Dr. Gray.
Oh, thank you. Yeah, thanks for the great talk, Andrea. I really like that. I was wondering on the topic of your second section, the paper by Clara. So for those of us who can't afford to run models at 2 kilometers, so for example, global models, do you have any hopes for parameterization? And it looks like these are pretty deep eddies, maybe in the bottom boundary layer. So the existing parameterizations for some mesoscale eddies that affect the surface mix layer are not kicking in, and those should be in like Ruth Morman's model. So do you have any hope for parameterizing those?
We've been working on it, actually. My former postdoc, Yang Wang, has published a number of studies on adapting existing ocean model eddy parameterizations to steep slopes, and with surprising success, actually. But the resulting parameterizations are somewhat empirical and yet to be implemented in existing Earth system models. So I think there is potential. I would say that Clara also tested using some excellent eddy parameterizations in her model to see if they might get around this problem of lower resolution models not capturing heat transport, and they did not. In fact, they made things even worse. They made the heat transport go the wrong way. Certainly what was available in this particular model to represent those eddies was not adequate. There may be scope for adapting existing eddy parameterizations to tackle this issue, but I would say that those parameterizations are still at the level of they've reached theoretical development but have not reached practical testing.
Thanks.
Yeah.
Hysteresis, I was very interested to see the hysteresis you found between the strength of the wind and the shelf water temperature. So hysteresis in some way seems to be a property, one way of explaining past climate change, especially rapid climate change. Have you kind of evaluated what you're examining here in the context of past climate change?
No, that's an interesting point, actually. No, we haven't. I mean, it's been a topic of interest to me that I've never had the opportunity to explore yet. How the process of melting this portion of the ice shelf or forming dense water would manifest in a climate like the last glacial maximum, where the geometry of this whole region is very different because of the expanded extent of the ice sheet. Over those timescales, you have to think about, you can't get away with what we've been doing and pretending the ice sheet is static and letting the ocean interact with it, and so I think it's a very interesting question. I think I'm too stuck with the simpler question of just how did dense water formation even work at the last glacial maximum when the geometry was very different. And it's tempting to just launch in and try and simulate it in a model, but I worry about how well constrained the atmospheric forcing or ambient ocean state would be to try to whether the answer would be meaningful if we did. So yeah, I think it's a great topic, but I worry that I don't currently see a route to addressing it that I could be confident with. Yeah.
I can see the question in this space right now is whether or not the feedback is positive or negative. So yeah, there's I can see why you don't want to also go back in time.
I want it.
You want
But I
to,
should.
Yeah, I have a couple of questions. So, the first one is overall the sensitivity to the meltwater is a bit surprising because we're talking about trickles there, where the fluxes are really sped drops, and the change in the meltwater production is also a fraction of that, whereas the general part of circulation around the Antarctic, some of these heat fluxes are 10 times, 100 times larger. So I wonder if you can comment on that. And then the second part, which is a bit detached from that, is in order to model this heat transport onto the continental shelf and non-continental shelf, you have to represent the winds correctly in the models. And I would like to hear your comments on how well the current climate models are representing the wind regime, especially in the Southern Ocean. So first, the freshwater being such a trickle, and then the representation of winds.
The qualitative answer to the first question is that I wish I could have a better handle on the numbers in my head in this moment, but it does turn out that if you calculate the amount of fresh water that you're injecting, and inject it into a realistic volume of isolated shelf water, say it's informed in front of the foot from the ice shelf, the dilution is sufficient to reduce the salinity by enough to make it less dense than the warm waters offshore. And in fact, that's explicit. I mean, the conceptual model contains explicitly calculates that dilution. I didn't write down the equations in the slide for brevity, but for sort of realistic numbers, it is enough. Is the short answer, and I would like to be able to just snapping off numbers for you. I don't have them in my brain right now. And the second question is how the winds are critical. Yes. How well are we doing with representing the winds? In IPCC class?
Projections, especially,
Ooh, I'm not sure that I can answer offhand how well we do with the winds and the projections. Yeah, good question. I mean, of course, we can't really know how well we do with the winds in the projections because we don't have any foundation for the future winds, but we could look at the spread, for example, in the projections, and off the top of my head, I'm not sure. Yeah, but that's an important point. Yeah, and yeah, I mean, like, is it within the uncertainty that the sense of the wind change could be the other way? I mean, one thing I would say is that Julia, one of Julia's other studies in her PhD, she actually looked at how the winds around the coast of Antarctica had changed over the last few decades. And the expectation was that the winds that blow to the west would have weakened because of this southward shift of the westerly winds and the latitude. But it turned out that in all the analyses, at least, they haven't. They basically not changed in the past few decades. So that did run contrary to our predictions, at least. And so it may be that the suppression of those westward winds around the coast is overestimated in future projections. That would be one plausible hypothesis based on that finding, but I really don't know what to say with confidence.
Last call for any questions for Dr. Stewart. Thank you, Andrew, for your great talk.